This is question 9 from the 2012 PAT. So in this question, we're asked to solve this trigonometric equation, or in other words, we're asked to find where this trigonometric function intersects the x-axis, because it's y equals 0. So if we first plot this function, we can see that it's a very ugly function, so it'd be very hard to solve directly. But if we zoom out a bit, we can see that it's at least periodic. We can also see that the graph intersects the x-axis at an infinite number of points. And this is probably why the question maker asked us to leave our answers in terms of sine theta, because these solutions are probably periodic in the same way sine is. Now the first thing we did algebraically to try and solve the question in the solutions video was rewrite cos squared theta as 1 minus sine squared theta. So if we plot that function, we can see that it is indeed the exact same function, so we've changed everything here. This is all fine. But what this function did allow us to do was substitute x to be equal to sine theta, so that we could obtain this quadratic. Now we've obtained this quadratic, our question now becomes when this quadratic intersects the x-axis. So you can see it does so here and here at 2 places. But we must remember that we've used the substitution x equals sine theta, and since we know that the function sine theta can only vary between minus 1 and 1, this means that we should only consider this quadratic in the region that x is between minus 1 and 1. So if we look now, the quadratic only has one solution because we've discounted the other solution because it was greater than 1. So now we know that the solution to this equation is sine theta equals around minus 0.6, or to be more precise from the solution video, sine theta equals 1 minus the square root of 5 all over 2, and we've discounted the solution for sine theta equals 1 plus the square root of 5 all over 2. Now one other interesting thing to note is that this quadratic seems to approach our original function in this region here, close to x equals 0. And why is that? Well, you've probably all heard of the small angle approximation for sine, and this is the reason why the graphs approach. If we look at the normal sine function, plotted here in purple, and compare it with the function y equals x, plotted here in black, we can see that as we approach x equals 0, these two graphs become essentially the same line. This is the same as saying that sine x approximates to x for small values of x. And this is the reason why this blue quadratic approximates our red trig function for small values of x, because we can say that in this function, for small values of x, we can turn the sine x's into x, and if we do that, we'll get 1 minus x squared plus x, which is exactly the same as this function here. So now we can see that even though the original trigonometric equation was very complicated, if we can find a way to force it into a nice polynomial, in this case quadratic equation, we can find the single solution to that equation, and then by reversing our substitution, i.e. letting sine theta equal the solution of this quadratic, we can obtain the infinite number of solutions to the original complicated trigonometric equation.